Okay, so you've just seen that amazing magic trick, and maybe even want to impress your friends by trying it at home, and hopefully you've written down all the steps involved in it and what you think is going on here. So in our notes, let's see what's going on. Let's draw a picture here. So there's a side view. Let's say here is this black line is the wall, and here is the balloon. And we saw in the video one of the first things that happened was we tried to put the balloon up against the wall, and nothing happened. What is that telling you? Well, it's telling you that there's no charge. Right? The balloon and the wall start off neutral. That's really the first important part of this demonstration. They start off neutral. Now remember, there's still billions and billions of protons and electrons inside of them, so we'll just draw some of them, our usual 5. There's nothing magical about the number 5, it's easy, right? So 5 protons, 5 electrons indicate that there's no charge in the balloon. We'll do the same thing in the wall, 5 protons, 5 electrons. There's no particular reason I arranged them this way, just to get a little variety, but they both start off neutral, 0 charge. That's why the balloon didn't stick to the wall. Great. Okay, so what happened next? Well, of course, the balloon was rubbed on her head, right? And then it was really to pay attention as to where the electrons were put, right? So the electrons were put on the balloon, but what side of the balloon? Hopefully you notice it was the side without the smiley face. We're going to call that the back of the balloon. Why did we do that? Well, we didn't want to smear the smiley face, right? But also it's important that the smiley face is there so you can see exactly where the electrons are and where they're not. So, right? So there were extra electrons placed on the balloon on its back. Now here's where you have to pay really careful attention. What part of the balloon was put up against the wall? First, you should have noticed it was the face that was put up against the wall, not the back. And what happened? The balloon fell. Okay? How did we be successful? It was successful when the back of the balloon was up against the wall. So here's the back of the balloon with the extra electrons. That's the side that was up against the wall. Here's the smiley face that was sticking out. And this is what's so important, that now we have our negative balloon stuck to the wall, because this is where we put the electrons on the back, and that's the part of the wall of the balloon that's up against the wall. All those details are really, really important. Okay, so here we have our negative balloon attracted to the neutral wall. Wait, that's not okay. Wait, negative charges are attracted to positive charges, but the wall is not positively charged. The wall is still neutral. Certainly we didn't rub our heads on the wall, that'd be kind of silly, but we didn't do anything to the wall to give it a charge. This actually shouldn't work. Okay, and here's where, I guess, the physics magic comes in. So the question is, why is this happening? How come the negative balloon is attracted to the neutral wall? So pause the video, take a minute to think about it, write down your ideas. Okay, so when we do this in class, one of the first things students realize is that a negative balloon has to be attracted to positive somewhere, and there are certainly protons inside the wall. And so some students say, I know, the protons are attracted to the balloon, they move towards the surface of the wall, and we cause this closer distance between them, so they must be attractive. But hopefully you remember, protons don't move. We've been trying to make a big deal about that, right? Protons are locked in place inside their nuclei, attracted to the neutrons by the strong nuclear force. Protons never move unless the entire atom moves, and that's not happening. But then hopefully you remembered, what is it that moves? It's the electrons. Okay, so the electrons in the wall, they sense the presence of this big negative charge, and they run away, and so they get pushed a little bit to the interior of the wall. And now look what happens. The surface of the wall looks like it's a little bit positive, the interior is a little bit negative, and now again proximity wins. The surface of the wall is just positive enough to attract the negative balloon. So here's what happens. Electrons in the wall sort of run away a little bit, leaving the surface a little bit more positive than it used to be, just enough to attract the balloon. And so we have this separation of charge. The wall is still overall neutral. There's no electrons gained or lost. Everything's balanced out. It's just a separation of charge. So the surface of the wall looks a little bit more positive than it used to be, enough to attract the balloon. In fact, if we were to take the balloon away, these electrons would return where they want to be, which is close to their protons. It's a temporary sort of situation. As soon as the balloon's placed there, the electrons are forced to the interior. This situation is known as polarization, a tiny separation of charge within the material. The molecules of the wall have been polarized. They don't have a net charge, just one side is a little positive, the other side is a little bit negative, and so we can get these forces of attraction even though the material is neutral. It's about its separation of charge. It seems to have a positive charge, at least on the surface. The word polarization you've seen before in terms of light, but don't worry, we're never going to mix and match. Now, let's go back to this idea of the electrons being put on the back. All these electrons are placed here and they're kind of close to each other, and they're all negative. What do they want to do to each other? Well, we know they want to repel, right? And so, left to their own devices, they should do this. They should spread all throughout the balloon. Some of them should end up over here on the smiley face side, which means the smiley face side should work when it's placed up against the wall, and yet it didn't. And when you try it at home, if you want to try it at home, you'll see it'll never work. The side of the balloon that doesn't have the electrons where you first place them won't stick. So the question is, if you put these electrons here, and they don't want to be clustered together, why do they stay clustered together? So pause the video and think about that. Okay, so hopefully you recognize, of course, the balloon is made of rubber. Rubber is a good insulator, right? So the insulating rubber keeps the electrons in place. This is why it's so important to see where we put those electrons. We place them on the back of the balloon, and even though they don't want to be clustered together, the insulator is, remember the insulating family, they're locked in place, 17 locks on the door, and so while they want to leave, they can't leave, and they're kind of stuck in place, and that's what's so important here. They're not free to spread all throughout. They stay where they're placed, and so the back of the balloon is the only part that really maintains the net charge. That's why the back of the balloon is the part that sticks against the wall.